So, hello everyone. So, am I being heard? Hopefully, yes. So, let me share my slides first. So, my name is Janardhan Silwal. So, I am one of the founders of Antarikchya Pratisthan Nepal, which translates to Space Foundation Nepal. So, we're just recently established here. So, we're working on uh, uh, space systems and CubeSats here in Nepal. So we're currently working on second satellite satellite mission for Nepal right now. So for this today's session, we'll first move on with my introduction and then the similarities that is between CubeSats and drone, as I'll be talking how about the uses of PX4 in CubeSat system to make a PX4 as a CubeSat operating system. So as we all know that PX4 is a flight software designed for drones. So first we'll talk about the similarities between CubeSats and drones, and then how PX4 can be used in CubeSats, and the current work that we are doing right now, and what the future would look like for a PX4 for a PX4 CubeSat. So basically, it's a PX4 and CubeSat, right? Okay. So now moving on to my introduction. So I schooled at 3 different schools. So at from Pragati Pathsala and Brahmkunta, I completed my high schooling, and from Kathmandu University here in Nepal, I completed my undergraduate in electrical and electronics engineering. So after my undergraduate, I was and am involved in 2 different projects. SastoCube, where you can see this picture of a SastoCube and top right. So that's SastoCube, which is an educational satellite that we did educational satellite of 1U standard. It's a CubeSat. So we designed for teaching high school students about what satellite is and how it works. And right now I'm involved in Nepali Sat 2 Padayatri as a project manager. So this is a project that is been done in collaboration with Thailand and Nepal. And as for the training sessions that I've taken related to this CubeSat, so in 2017, I took part in CanSat training. We'll come back to this in a bit. So it happened in IOE here in Nepal, Institute of Engineering. So that's about it for myself. So now this previously, so before continuing with this for the presentation, what I'd like to say, so before last year in PX4 Development Summit of 2020, so this Dr. Abbas Maske, who was then the PhD student at Kyushu Institute of Technology, Japan, gave a presentation about using PX4 for educational satellites in CanSats. So, and he talked about how PX4 was used in CanSat, which he designed the training for. So it was the training that I took part in back in 2017. So he was the one who supervised the overall training session. So there we used PX4 system. We used Pixracer for PX4, right? So there's Pixracer board. We use Pixracer as a onboard computer for CanSat, and then CanSat, and we just made a demonstrated CanSat using PX4. So, and he also talked about how in future CubeSat could use PX4 to replace it as a flight software, since there isn't any hard and fast flight software that has been dictated to be used for CubeSats. So in this presentation and our work, we are just continuing what he proposed then. So he's also currently we're also working under him right now. So we're just continuing his idea to use the PX4 in CubeSats, so to make the development of CubeSat easier, and then just reduce the entry level. So how as it is in drone. So basically everyone can make a drone if they have the PX4 supporting system easily, right? So, but that's not the case for CubeSat. So we're just continuing what he proposed to make it easier to make CubeSat using PX4, just modifying PX4 to operate on CubeSat 2. So now we'll move on to the next agendas. So we'll talk about how CubeSats and drones are similar with each other. So first, starting with CubeSat. So what is a CubeSat? So as seen in the picture, so this is a picture of CubeSat. It's a PWSat of ESA, so European Space Agency. So this is a 1U CubeSat, right? So CubeSat, it's 10 by 10 by 10 cm. So basically, it's length, breadth, height. So it's a little bit bigger than Rubik's Cube, and you can just fit on the in your palm, right, in your hand. Just carry it in your hand. And this falls under a nanosatellite category. So it's a nanosatellite. So there are different sizes of this CubeSat. So it starts from 1U and it can go up to 24U. So it's like for 1U CubeSat, this is a 1U CubeSat. So if you stack two of them, so the total dimension being 10 by 10 by 20, so that becomes 2U. And if you stack one more on top of it, that becomes 3U. And if you just keep on stacking and up to, you can go up to 24U in size for CubeSats. Until 24U, it still falls under CubeSat. So the standard size for 1U is 10 centimeter by 10 centimeter by 10 centimeter, XYZ. And 1U CubeSat, it weighs less than 1.33 kg, so it's pretty light actually, so not that heavy for a satellite. And the total average power for 1U is 1 watt. So the total average power, so system is designed to be under 1 watt actually. So because that's the total theoretical maximum power that it can generate, because there are less space to put the solar panels. Of course, we can increase this by using deployables, but if we don't use it, just in the standard, you don't use deployables. So that's the 1 watt power system in average. So that everything runs under 1 watt. So this is this swap requirements. We call this size, weight, and power requirements, which defines the standards for the CubeSat. So CubeSat. And on this picture, you can see this is the P-pod integration. So it's basically the deployer for CubeSat. So they can stack up to 3 CubeSats, right? So this is for 3U unit. So you can put one 3U satellite CubeSat, or 3 1U, or one 1U, 2U, or one 2U satellite in this P-pod. So its inside dimension would be, so this I just leveled it outside, but the dimensions is the inside. So it's 30 by 10 by 10 inside. So we can put a 3U satellite inside there to deploy it from either from a rocket or from International Space Station ISS. So moving on with CubeSat. So CubeSat was initially developed to be used as an educational tool for teaching students about space systems, right? Space systems. So, but it has been and can also be used to test new systems, that new sensors and new technologies that one might want to use in space. So at a low cost, because if you want, because earlier, let's say if we want to send a satellite now, big satellites, it's going to cost us millions of dollars, right? But for CubeSat, it doesn't cost that much. You can just send on 100,000. You can, it's comparatively cheaper. It's a cheaper alternative for the $1 million satellites, right? Of course, some of the CubeSats are also millions of dollar CubeSat, but on average, it just costs far less to test a system on a CubeSat than to build a big satellite and test the system, because you don't know if it's going to work or not. So CubeSat become the new alternative for the researchers to test new system. And also, it can also be used commercially actually. So which is being done by Planet Labs. So you can see on the bottom left picture, there's a B14. That's a latest version of the Planet Labs satellite. It is used for Earth observation. So they just takes the images of the Earth, and then Planet Labs is using it commercially. So they are just taking a up to 30 centimeter resolution image of the Earth, and then they're just compiling it and selling it to the consumer. So you can also use CubeSat commercially. So until now, Planet has launched 475 CubeSats of 3U. So okay, this is a 3U CubeSat. So they have launched it 475 till date, and as of August 2, and are also still planning 150 more, according to Newspace, right? So CubeSat has now not only been used as an educational tool, but it has even moved from testing new system for researchers to even the commercial companies launching the CubeSat since it was first standardized. So so that's the CubeSat. So here in this figure we can see, so CubeSat, the CubeSat, the term, it is coined early. It started, the idea started as early as 1999, but it was not until 2011 12 that it started to pick up momentum. Actually, you can see the graph. So it was only after at 2010 11 that it started it started coming to the widespread use, and then just its use grew rapidly. And at now in 2021 we can see that 1638 CubeSat has been launched. This, of course, this includes the launch failures, but just imagine, initially there were just 2 or 3. Even in 2010 there were just 81 cubes, 81 nanosatellites right now. But in 2021, just the CubeSat that was launched amounts to 1638. Now that's a huge growth. Huge growth. It's just growing, and then it is even expected to grow more in coming future. So this shows that the CubeSat is being just the launch of CubeSat, that it has been it's going exponentially, and then more and more universities and students and companies, they are just making their own CubeSat, and then they're testing new system. Even some of the countries, they have just made their first satellite, which is a CubeSat 2, including here in Nepal, right? And now that the previous graph was about how the CubeSat has been used over the years, and while this shows us that how many CubeSat could be launched and are planned to launch in the upcoming days. So as you can see, there has been exponential growth on the CubeSat launched, right? So that had been launched to the orbit. Even in the coming future, so in 2021, so they just predicted that there are going to be 750 CubeSat launched, including the already launched ones. Just you can see in 2020 it was just 163, just increasing, and even in 2022 they are it's just climbing upwards and upwards. So what this shows us is that we can use this CubeSat. We can use for PX4, if we can make it into a operating system that supports CubeSat, then I'm pretty sure this number are gonna go way more than what it has been predicted, because currently with the high entry barrier of having a not specific, not a no common software, and then just a tedious design process, and then development testing, even with all those tedious process, the CubeSat user is growing so exponentially. Now imagine what would happen if there was a system, there's operating system which would just say, okay, you just download the software, you just load it into your system, and then boom, the CubeSat's ready. So if that would happen, then the numbers of CubeSat that would be launched in the near future, in the coming days, would just skyrocket than what has been predicted by nanosats.eu. So now talking about CubeSat, so of course we need to talk about the design process, and then what are the similarities between the drones and CubeSat. For the drones, for the software designed for drones to be used in CubeSat. So there, in CubeSat design process, there are typically 6 milestones, or let's say checkpoints. We like to call them checkpoints. So, and the development time for a typical CubeSat is typically from 18 to 24 months, most of which of course take for the software designing. So initially we'll just start the kick off the project, and so there will be the kickoff and then operation phase, right? So kickoff, we just design the CubeSat. In operation, we just operate after it has been launched and deployed. So typically a CubeSat operates for around 2 to 3 years, its lifetime. So, but that is also considering, but it can increase or decrease considering the orbit that you launch into. So we're just typical launch, one CubeSat are typically launched in 400 kilometer orbit, so that operates for around 2 to 3 years. So it just varies. So after the kickoff, we'll just sit down together. All the design team will sit down and just discuss what the CubeSat is to be designed for. So we'll just define a mission for it. So what the CubeSat is to do, what it will do, and how it will do it. and then just all the missions will be defined. And after the missions are defined, the system also needs definition. So how the system is going to work, what kind of systems it's going to use, what is the, let's say for example, what could be the current limitation, what could be the power, what is the voltage, those things. So they will define the system, and after the mission the system will be defined. And after all the systems, after all the definitions for all the systems of CubeSats are ready, we'll go with the definition review. So we call that mission definition review, MDR. So it's so this reviews, so we just sit down the experts and then all the design team, and then we'll just review, okay, is this okay or not. So of course there's going to be stakeholders too who are investing in the satellite, so they also want to their own mission to be done. So they also sit down there and just discuss, and then if needed, just edit and redefine the missions. So that's the mission definition review. After which we will start the breadboard model fabrication and operation. So here we'll just since we already have the system defined, then we will know what components we need, what we are gonna do, and what we need to buy. So we'll just get all those things ready and then just test everything, right? So if it works or not. So does that work? Okay, it's work, that's fine. We just test everything, and then we'll just make a small soft system for the CubeSat, and then just operate them individually. So that's the breadboard model fabrication. And then we again do a design review. So this usually takes about 4 to 5 months for this process. So that's preliminary design review. We call it PDR. So after PDR, we now move on with the engineering model design and integration. So here we design all the system, this tight pack, and we actually make a complete CubeSat here in this phase. So after PDR, we move on to making a first prototype of the CubeSat. And then we'll do the testing of the model, engineering model, since it's gonna need to survive the harsh space environment, the launches, and all the shocks that, as well as the radiations, the temperature variations. So we for that we need to rigorous testing. So we just do the first environmental testing on engineering model, and after the test report comes out, then we'll just do a critical design review. Here we'll see if the design system passes, is ready to move forward, or do we need to design again in the critical design review. We just go through everything, so everything, right, everything, and then reiterate it if needed. And after the critical design review and then the changes review, the flight model will be fabricated and it will be tested. So then it will be like the final model that is to be launched in this space. And of course we also do the environmental testing for this model, as we did for engineering model previously. And then we'll have flight readiness review. So this gives us the final review. So this includes the safety reviews as well as all the test results and everything. After the flight readiness review, the CubeSat will be delivered to the launch provider. So they will just launch the CubeSat either from the ISS. They will launch the ISS and deploy from there, or it will be launched from the rocket. So there are two options for launching CubeSat. So after it's deployed, then it will just go into the operation phase. So now that was the operation, the design process for the CubeSat. So now let's see what the design process for the drone is, and what are the similarities between the two. So this so I'm considering the design process of the squadron system here. So they have 5 milestones for the, you can see that there are 5 milestones here for the design process of the drone development process. So now what are the so there's identification of use, proof of concept, prototype development, tests and validation, and industrialization deployment, right? So let's see the similarities between the CubeSat design process. So first is identification of the use of case. So this is equivalent to our mission definition of the CubeSat, and then of course we have a mission definition review. So which should also, I believe, be the case in the drones, because after you identify the case, then you need to just see, now is that okay or not. So in that case, so that matches with a CubeSat mission definition review. And then we go for the proof of concept for the drone, right? So we just check the feasibility of all the units. So they just check every unit, is it functioning, is that functioning or not, and then are there any developments that we need to do, are there any changes we need to do. So that's what we do in proof of concept, and that matches with our preliminary design review. So after all the proof of concept has been done and demonstrated, then we move on with the actual prototype development, right? So it will be actual working model, working drones. So in that case, it matches with our critical design review, where we develop a complete engineering model and then present. So we just see if it works or not. So now that's the prototype development and critical design review. So now after we do the prototype development, we go with it will be iterated, tested and iterated and all, and then we come at tests and validation point, where we'll just see, okay, now is it ready to be launched in the market or not for the drones. So that also matches with our flight readiness review. So that's the flight readiness review for CubeSat, and test and validation point for drones. So now then after, there will be deployment of operations. So the drones will be industrialized and then they're just launched in the market and consumers are going to use it. And in our case, the CubeSat would be launched, and then we're just going to do the missions. So in that case, we can see that both the design process of the CubeSat as well as the drone are similar to each other. So that was one of the motivation behind why we thought, why not use PX4 for CubeSat too, since the design process of hardware, so the design process of drones and CubeSat is similar. So if we alter a little bit in the design process for the drones and a little bit in the CubeSat, then maybe you can just make an operating system that you can use a PX4 based operating system for a CubeSat to just make it easier for us to make a CubeSat. So that was the motivation. So now talking with the drones and their similarities, even if we consider the structure, if we consider the overall this drone system, we can see that the drones have their own airframes, right? In PX, we get to choose the different kind of airframes for different types of drones. Similarly, CubeSat has their structure, which holds everything in place. So it's like you have different types of structure for different standard of CubeSat. So for 1U, you get one structure. For 2U, it's other structure, and for 3U, it's other structure. Similarly, they are different for drones too. So in a sense, they're both same thing. So they're just holding everything in place rigidly, and there's not the components are being held and then they're operating nice. So in that case, both of them are same. As for the flight controller, we can see in image that I just demonstrated Pixracer, because that's what we're inspired with. Our team was inspired with, as we had access to Pixracer due to the CanSat training that was done back in 2017. So in drones, there is the flight controller. For now, let's say it is Pixracer. So the Pixracer is the flight controller, which is equivalent to the onboard computer in CubeSat. So we can also call that flight controller, or we like to call it different names. So it's like onboard computer, data handling, and other variation, but basically they do the same thing. So they just controls everything of the CubeSat. So onboard computer and the flight controller. So that's also the same there. And even the drones, they could have their own payloads, and then they could also have their own missions that they had to execute, which is the case again for our CubeSat, because we designed a flight controller and other communication system, and then we just put our payloads to the back again along with them. So it's like, if we just tweak a little bit here and there, we can get both the CubeSat as well as the drones to match. And again, for the drones, we have the telemetry, which they communicate with the ground base station, or let's say ground station in this case. In this case, it's a mobile phone connected with an antenna or telemetry module, right? So that's the communication system. They also have their own remote data receiving system. So the same is true for CubeSat. CubeSats have their own communication system, which they use to communicate with the ground station to receive commands and then send data, get data. So and then of course in the recent days, as you could see from the graph over here, the CubeSats with nano satellites with the propulsion system and actuators are been getting popular slowly. So in a sense, drones also, they have their own actuators. So we can see that overall the structure as well as the build and the overall system blocks of the CubeSat and drones are similar. So what we thought was to use drone software on CubeSat, since also the drone uses COTS component, right? So it's consumer of self components. So it's the same case for CubeSat. We don't use any specific space grade or specific chips or systems designed for space. We just use whatever there is in market. We just use that and make a CubeSat. So in a sense, both are the same. So they are using same kind of components just for different purpose. So what if we make the same? What if we align their purpose together and design a common system? So that is what the idea is. And among the drone markets, so right now the drone market has the coming of this PX4 Autopilot and similar system just reduce the entry level for designing and making a own drone for hobbyists and everyone. So that has got on the, and even the commercial market, commercial firms are adopting this kind of systems like PX4. So the drone market has just gone high and high. So now it's gonna be almost saturated in quite a few. So in a sense, if we use the drones, correct drone resources for the drones to make it into a CubeSat system, then the drones market are gonna find a new market, and then it's not gonna be saturated, right? Saturated. So in a sense, it's like a new field for the drones to move to the CubeSat, giving them a wide view, I'd say. And also we can just package once the software is ready, you can just package it and then sell as a product too, actually. So it's like a new market, and for the CubeSat, it's like you get a easy way to build a CubeSat and more time faster. So it's a win-win situation for both communities. So now let's compare. So what is the difference between the drones and CubeSat now? So we just talked about the similarities and all, but now let's come to the differences that is between the drones and CubeSat currently. So for the drones, we can see that it already has a mature system for development, as the market is almost saturated, and almost anyone with a little knowledge can just make their own first drone. Of course, it may not be advanced and do all the advanced features, but just for making a drone, I'm pretty sure some guy with just little knowledge and then a little bit of internet can just make their own drone if they have right components, right? But for CubeSat, it's a highly experimental development process. So even if you already have a reference CubeSat to look into it, because the purpose of CubeSats are going to be different, the missions are going to be different, so you have to redesign it again. So you can just take a reference but not copy it. Even if you copy it, there are going to be problems, and then you're just going to have to design it, to test it, and again redesign it. So it's like a highly experimental development process for CubeSat, and that is also what takes a lot of time, actually. So it takes almost 2 years for a CubeSat to be ready, but not for a drone. You can just make it in, let's say, 1 or 2 days if you have the components available. And for the drone, there is already a easy to use open source flight software. It's software, so you can just make a, let's say you just want to make your own board, you just see the references and then design your system and then just upload the, let's say, open source, in our case, let's say PX4, and then boom, the drone's ready. But that is not the case for CubeSat, because each software for CubeSat, there's no specific software. Let's say there isn't even software, it's just individual coders typing out their own codes, individual teams doing their own coding for the system MCUs, right? So there's no specific software, or even if there is, it's just a specific functionality software, like we saw the Planet Labs CubeSat earlier, right? So they have this massive constellation of more than 400 satellites, 400 CubeSats, and they have their own softwares to just take the image and then just send it down. But now, if you want to if you don't want to take the image and do other thing, but want to use the software that is using Planet Lab, okay, now Lab, if it's available, now that is not going to work. You have to design your own software. Okay, sorry for that. Design your own software. So in a sense, there's no software for CubeSat, and then you have to design it completely from scratch. It's like, even if you could use it, you have to modify it massively. So it will take a new form, it will be completely different from what it was originally. So that is also one of the challenges of making a CubeSat. It takes a lot of time to make the software right. And the drones system, it's modular, and you can just and the software, it's easy to add, and the software making it is easy, and also you can just add or remove payloads easily in PX4 or the similar systems, right? Similar systems. But in case of CubeSat, if you need to replace a payload, then you need to redesign again whole system from scratch again. So that's one of the disadvantages of the challenge of the CubeSat designing. So for the drone, it's easier since it's modular. And also one more advantage of the drones for designing a drone system is it has got its own simulation environment like Gazebo. So in that case, we can just simulate whatever we want to do, and whatever system we want to add to the drone, you can just design it, and then you can simulate it and check for the errors that may happen. But there is no such softwares for CubeSat, so it's you have to do everything manually. You just design the system, fabricate it, and then run it, and then see in the real hardware. So if there is any problems, then you can do it from the start. So it's like, so it's costlier than drones, even though it's cheaper, but it's costlier than your general drone making process. It's costlier and it takes more time, because if there is any mistake, you encounter later, which are obviously going to happen, so you have to do it again from the start. And also for the drones has got massive community of synchronized users. So if you can see the PX4 community as example, so it's quite massive, and then everyone's sharing information with them, and that they're linking and helping each other. But that is not the case for CubeSat. There's just a small fragmented user base, and they are not synchronized with each other, so it becomes a little bit harder and more challenging to get what you are doing across to other people. So it's like two people might be doing the same thing, but that would not be the case in the drone. Same thing, and they might be having some troubles, which could, if communicated, help each other in case of CubeSat, help solve each other's problem in case of CubeSat, but that is not happening right now. So that's another disadvantage. So in a sense, if we could take the advantages that the drone system and the overall process has to mitigate the disadvantages of the CubeSat, then that would just boost the CubeSats and its use everywhere. So now let's talk about PX4 and CubeSat. So we just saw the similarities between what the drones is, what CubeSats and drones, and the differences. Now let's see what the PX4 CubeSat could look like. So first of all, so for a PX4 system, as I repeat again, so we are inspired by this Pixracer version 1.0, right? As we here in Nepal got exposed to it, myself personally, during the CanSat training. So you can just look for it on the last year's slides too, given by Dr. Maske. So this is a well-tested system, I would say, because it's just it's just getting reiterated over and over, and all the bugs are being removed, and then the testings are being carrying on even as we speak. Someone might be just developing their own version of PX4 too. So in a sense, it's a mature, well-tested system. So, and it is modular. So the best thing about this is it's modular and it's easy to customize according to the needs. So if you want to change, remove, or add something, you don't need to redesign everything. You just remove the block of code, and then that's it, done. So that's the best part about it. So if we can design PX4 in such a way that it can be used in CubeSat, then later on, if we don't want some system, then we can just remove the code for that and then just run it, and that would work. And if you want to add something, just plug it in through the bus, and then it works. So in a sense, that's the advantage that the PX4 has over the current system for CubeSat. And of course, the other best thing is the large user base community. So in case we need some troubleshooting or debugging, then we can just post, and then we can post some questions, and we can get help from everyone. So that's the other advantage. We've got the PX4 and drones system as a large user base community. And especially nowadays, especially the PX4, it's adaptable to STM32 MCU series, right? And now it's CubeSat are using it more and more. So even the commercial companies which just manufactures CubeSats, payloads, and boards, and even CubeSat itself are aligning. We can see the use of STM32 more and more these days. So they are just using STM32 chips. So another advantage is that STM32 supports PX4 system. So in that sense, that's also another advantage for us to make PX4 adaptable in CubeSat. And the other thing is we can simulate the system that we designed before actually implementing it. So So some of the errors we can just find out while simulating. We can just see what errors we can encounter if we make the system, right? So that would help us. That will help us reduce the cost for manufacturing, actually, as well as reduce the time it takes to debug the code, because once the whole system is running, it's very hard to debug the code. But if it's in simulation, you can find exactly where it went wrong. So that is also another massive advantage for us. And you can see the PX4, then the far right picture. I've just circled the 3 circles, right? So the bottom one, it just highlights the PX4. So that would be the OBC. So this again repeating, just a reference for the PX4 Pixracer system. So, and the top one, the ACSP module, would be the EPS module for the CubeSat, the electronic power system, which just powers the CubeSat. In our CubeSat, we call it EPS. So for the drone, that would be the EPS too. So it's like you got EPS, you got OBC, and for, you can say for GPS, okay, let's say it's for attitude control, or let's say it's a payloads, and you can add external sensors, so that would be the payloads too. So in a sense, the drones that we are using right now, in a sense, is like a CubeSat, just it's not packed into a cube. It's like it's just spread and then just running. Just it is not work. It's designed for Earth, not for space. So that will be the difference. So once we design it to work in space now, that would be the CubeSat. So that's quite a lot of potential right there. So what would a PX4 CubeSat be like then? So first of all, it would be modular system. So it will have everything modular. So you just, if you want something, you just put it. If you don't want it, you just remove it, right? So that would be modular. And the bus system for the CubeSat would be fixed, the fixed bus system software. So it's like a bus system includes EPS, electronic power system, onboard computer, and communication. So for these 3 systems, so it would be, they would have a fixed software. So we just upload it and then be done with it, right? So, and the CubeSat developers only need to focus on their own payload only design the payload and the interface for the PX4 system, and that payload, just design that only. So that would allow them to design their most missions or payloads more intricately. And also it would allow for the developers to focus more time on the for developers to focus their time more on testing of the CubeSat, which would ultimately increase the success rate, which is actually quite low, that not much high. It's not that low, but neither is it high actually compared to the drones. So, and it would of course, and obviously the CubeSat PX4 CubeSat would use a consumer off-the-shelf component. So it's like the normal daily component that you find in the market. You just use that and build the CubeSat. So that is what we've been doing now, and that will be continued. And the software in the loop simulation, SITL, that is available for drone system would also now support the simulation of the CubeSat in space. And that would give us the chances to find the errors before we actually implement it and send it. So this will also help us increase the success rate, as well as reduce the time and the expenses that we invest to design the CubeSat. So this the plus point for making the PX4 compatible to with the CubeSat. Here you can see in the far right, you can see the picture of the CubeSat. That's a Nepali Sat one, and the bottom one is the board that we are currently working on. I'll come to it later. So now, what are we doing right now? So we just got an idea to use the PX4 for the CubeSat, right? So now, what are we doing to just make it possible then? So for now, we have a 3U CubeSat, right? So we can see the picture in it's just a rough sketch, but that's the CubeSat that we have right now. So that would be launched, that is planned to be launched in 2022. And for this particular CubeSat, we are just designing a payload. You can see it pointed by the arrow here. Let me just turn on the pointer. Anyway, that's it. So that's the this is the payload that we have right now. We are designing that payload. So the payload will be 100 by 100 mm. So that's the typical size of the. So for 3U, it's as we talked earlier, for 3U, the size would be 100 by 100 by 300. So we're just designing a 100 by 100 mm board. That would be the payload for this particular CubeSat. So For now, we have just loaded PX4 firmware into this board, but we have not introduced any form of modification in the PX4. We're just using it as it is in for Pixracer. So as it is for Pixracer, we're just taking the same firmware and then we're just putting it inside the board. So this is for the functional test of the board. It's like before we actually use it, we need to verify if it actually works in space or not, right? So that is what we're doing right now for this board. So we're testing if the Pixracer system, that's the total compatible hardware and its software, can operate in space over the time without any problems, or if there are problems, what kind of problem there would be. And so we're just collecting the data basically for now. So in this initial step, we're just sending the PX4 as it is without any modification. So it will be used for its functional test and to see if there would be any problems. If there are, then we can just work on it to solve it, and if there isn't, then that's good news for us. So then we can move on with the other future work. So for now, what we're doing is we just use the PX4 compatible hardware. So it's inspired from the PX4. You can see in the bottom picture, we just hooked up a STM32 MCU board and then a PX4 together, and then we're just monitoring PX4's the Pixracer operation. So what is it doing? Is it okay or not? And then we're just collecting the data. So normal data like this gyro, accelerometer, and other data that it can provide. So we're using the Mablink protocol for this. So it's Mablink protocol, and then we're just communicating with the PX4 system. So we'll just be doing a functional testing of PX4 in space. So since especially since there is this South Atlantic anomaly in the space, there's the area of high radiation density. So there's the South Atlantic anomaly. There is quite a bit of radiation in that space. So what we want to know is, will the PX4 system, while passing over the high radiation area, still work as it should work or not? So that is our major focus here. So that's why we're doing the functional testing of the PX4 in space without any modification. We'll be collecting housekeeping data from the system as well as from PX4 and check the operations. So at regular interval, we'll just run it and then check this operation and then system and verify it works. So if it works, then we'll move on with further. So this is the center board, is the CubeSat payload that we are designing right now. So what we want to do is, we want to design it in such a way that it would be like a fusion of CubeSat, the PX4 Autopilot, as well as a drone. So it will be like this new system, right? So it's also like a drone. The process also goes as it is a drone, and it's also a CubeSat, and it also has a operating system such as PX4 or middleware. So it's like we combine the CubeSat, PX4, and drone system. So, and the end result would be, we get to rapidly develop the CubeSat. Even the new series of MCUs that ST is releasing, the STM32 new MCUs, so we can just rapidly prototype for them, right? Rapidly prototype for them for new modules for them, as the PX4 supports STM. So we can just rapidly prototype for newer MCUs. And of course, there is support. Of course, the PX4 has got its own support for previous older MCUs too. So this will ultimately increase the success rate for our CubeSat and make the CubeSat easy to be designed. So, and the ultimate thing that we did is we just ripped the PX4 and then removed the components that were unsuitable to be used in space or that we did not require to be put in our board. And then the remaining components that could be used and were needed, we just embedded it in the payload for the CubeSat. So that's the CubeSat payload. So in the board, in the section of the board. Of course, while we're not only doing the PX4 mission, but one section consists of the PX4 mission. So now, what would the future look like then? So this is what we did. So what would the future be? So let's say in the coming days, what would we do after we complete our current work? Then after we just verify that PX4 is operating normally in space and all, then we move on with the active modification of PX4 firmware. Since right now we are not doing any kind of modification, we'll make the firmware more suitable for CubeSat and include the airframe for the CubeSat too. So for the CubeSat in the software, as you can see in Cube Ground Control, you can just select the airframe of CubeSat, and that's the CubeSat. And also we'll since the attitude determination system for CubeSat and PX4 are different, we'll add a CubeSat attitude determination sensor into it, and also reduce the prototype and the designing time that is required for a CubeSat. So that is and designing time that is required for CubeSat, and increase the testing time. So this would ultimately lead to bridging the gap that is between the drone development community and CubeSat development community. It's just like a bridge, and we'll get more ideas and new things for us. So that's about it from me. So if there are any questions, then please go ahead. Okay. Okay, so okay, so regarding the question from Mr. Zuka, so the CubeSat, while there could be some common functionalities, but inherently all the CubeSat would be designed in their own way, own approach. So it's like they have their own. They might. It's like they have the own similar end result, but they take a different approach. So it's like a different. So it should be different for right now. So even if they take a picture, if two CubeSat they are taking the pictures, but they might take the pictures in different way, in different form, and so it would require different design. So ultimately it leads to different systems. Okay. The title of your paper from slide 24. Okay, let me just present it again. Slide 24. Can you paper from slide 24 in questions? I don't think I have a slide 24 slide. So Mr. Adrian, can you just please repeat what we want? So there's no slide 24 for me. Okay, and we'd also like to ask help, of course, for me as for Mr. Adrian Wall. So okay, so for your previous question about how the third parties could contribute in a kind of open innovation approach to our research. So it's like right now we're not doing anything for the PX4 because fundamental reason is we don't know how to just breeze into the designing of the airframe, right? So or similar system. So we're just right now experimenting with the system as it is. So in a sense, it would be helpful for us if the current community could just let's say design a CubeSat airframe or other system that could you be used in space. So in a sense, it's like it would be great actually. So if there are any more questions, then please. Otherwise, then I think I am a bit over the time, so I end this my session. Thank you, everyone. Thank you for listening to me. And if you have any question, you can just email me. I think I have my email. I'll just leave it here in chat. So it's you can just email in my email. I'll just left my email address in chat if you have any more questions. Thank you. Have a good day.